Alright, in this problem, we're going to be talking about these particles. Particle P moves along the x-axis such that for time t is greater than 0, its position is given by 6 minus 4 e to the negative t. Particle P moves along the y-axis such that for time t greater than 0, its velocity is given by 1 over t squared. And then at time t equals 1, position of the particle is 2. This first problem asks us to find the velocity of particle P at time t. I think before we start this problem, it would be really good for us to discuss the relationship between position, velocity, and acceleration. So the derivative of position is velocity. The derivative of velocity is acceleration. And you can sort of think of this as a vice versa as well. So the integral of acceleration is velocity, and the integral of velocity is position. So that will really help us with the parts of this problem, because it's going to be asking us to move between, position and velocity and acceleration. So understanding what that relationship is really, really important. So this first problem asks us to find the velocity of particle P. Well, we have the position here, so what that means is we're going to be taking the derivative of our position function. So the derivative of 6 minus 4 e to the negative t. So remember that the derivative of e to the x is just e to the x, okay? You might have seen that meme where, someone tries to take the derivative of e to the x and it's unstopped. It's just e to the x again. For our position function, we have something that's very, very close to just e to the x, but we have e to the negative t. When we have an equation that isn't exactly e to the x, we have like derivative of e to the k times x. The derivative is going to end up being we move that k down, so now we have k times e to the kx, okay? So that's exactly what we're going to be doing when we take the derivative of this position. So the 6 goes away because it's a constant, so we don't really need to care about it. So we have minus 4 times, you can kind of think of this minus t as minus 1 times t. So that's going to be our k here, so we're going to move the minus 1 down, and it's going to look like that. So we're going to be multiplying it by minus 1 e to the negative t. So then these two negatives add up to be a positive. So our velocity function is 4 times e to the negative t. Okay, next problem. We have find a of q of t, the acceleration of particle q at time t. Find all times t for t is greater than 0 when the speed of the particle q is decreasing. Justify your answer. So there's two different problems here that we kind of need to do. The first one is finding the acceleration of particle q at time t, and this should help us out with the second part of the problem, just finding when the speed is decreasing. So as I mentioned before, we need to go from velocity to acceleration, so we're going to be taking the derivative of this as well. So our velocity q of t is 1 over t squared. So we can rewrite that as t to the minus 2 power. Remember that if it's the denominator of a fraction, we can just add that minus sign to it to get it in the numerator. So that's the same thing. And then we just use our product rule. So we bring that minus 2 down. And now we have minus 2 times t to the minus 3 because we subtracted 1 here. So this is our derivative. We can rewrite this as minus 2 over t cubed. Right, we're just doing the opposite of what we did here when we converted it to t to the minus 2. We're dropping it down into the denominator again so that we don't have any negative exponents. That's the answer for the first section of our problem. Now we need to find all the times when the speed of the particle is decreasing. Speed, here's where we kind of need to understand the relationship between velocity and acceleration a little deeper. So we would say that our speed is decreasing when the velocity is increasing / decreasing, and the acceleration has a different sign. Okay, so if the velocity is increasing and the acceleration is decreasing, or if the opposite is true, if the velocity is decreasing and the acceleration is increasing. This should make sense. Let's see. Draw a little car. that our car is moving forward, so our velocity is positive, it's greater than 0. And then let's say we hit the brakes, so now we're accelerating in the opposite direction, we're decelerating, so our velocity, or not our velocity, our acceleration is less than 0. We would say that our speed is decreasing here, so speed is decreasing, right? And this is good because if your speed wasn't decreasing, you would probably just ram the car that's in front of you if you're, say, for example, stopping at a stoplight. The same is true for the opposite situation. So if you're backing up and let's say your velocity is less than 0, so you're going in the opposite direction, and then as you're backing up, let's say you hit the brakes again, so now your acceleration is greater than 0, right? You're accelerating in the positive direction, so then your speed is going to decrease again. Speed is decreasing. This is also good because let's say, for example, you're backing up out of your driveway or something and a car is coming, so you hit your brakes, you accelerate in the positive direction. If your speed wasn't decreasing, you would just end up hitting whatever car was behind you, and then you'd have an angry neighbor, and then you'd have to settle that dispute. Either one of these is happening, the speed is decreasing. How does this apply to our situation? Well, what is the acceleration of our particle? The acceleration we solved for here, it's minus 2 over t cubed. And then our velocity at the same time is going to be 1 over t squared. So if we compare these two, you'll sort of notice something interesting. So notice the signs of these two equations. So for our acceleration is always going to be negative, regardless of what we put in t, because we have that negative out front, and you can never get a negative value from a cubic, so t of 3 is always going to be greater than 0. It means the acceleration is always going to be, will always be negative. And then here, notice you have a positive sign. So there's no number you can use for t in the velocity function such that you're going to get a negative number in the denominator, okay? Our velocity is always going to be greater than 0. So velocity will always be positive. What this means is since we're looking at all the times for t is greater than 0, it means that the speed of the particle is always decreasing. So we can add that in. Speed is always decreasing because the velocity is increasing. The velocity is always increasing. It's always going to be positive. And the acceleration is always negative for t is greater than 0. Okay, so this is kind of going to be our final answer for the second part of the question that asks when the speed of the particle is decreasing. The reason why is because of the signs of our velocity and our acceleration. All right, moving on to the next problem. I've just copied the little segment in the problem about particle q, just so we have an easy reference. So here we're being asked to find y of q of t, which is the position of the particle q at time t. Remember what I said about the relationship between position and velocity? So we have our velocity function here. If we want to go back to position, we're going to need to integrate. So to find yq of t, that's going to be the integral of v of q of t, which is the integral of 1 over t squared dt. All right, finding the integral of the velocity equation, we can rewrite this once again to be t to the minus 2 power dt. This just makes it easier to integrate, in my opinion. So we just use power rule here. So minus 1 plus 1 times t to the, you add 1 up top as well, plus c. So that is going to be minus 1, so just minus t to the minus 1 plus c, which is equal to minus 1 over t plus c. You might be tempted to just leave it like this, but this is not a valid answer. You have to solve for your c, okay? The reason why is it's a constant of integration, and asks us just to find, the position, and it'd be weird to just leave your constant in there. So you might be wondering, wait, how am I going to solve for this? Well, remember, we're actually given the position of the particle at time t equals 1, and that's going to be 2. So what we can do is, remember, we were solving for y, and we got it in terms of t. So we can set the left side of the equation equal to 2. So our point is 1, 2. And then we can plug in, so this would be our y, this will be our t. So we can plug in 1 for our t, like that, plus c. So now we're going to get 2 is equal to minus 1 plus c. Add 1 to both sides, 3 is equal to c. We're going to get that y of q of t is minus 1 over t plus 3. Because we solved for our constant, you can also rewrite this as 3 minus 1 over t if you wanted. Right? And that's our final answer for part C. Moving on to part D, we're saying, as t approaches infinity, which particle will eventually be farther from the origin? Give a reason for your answer. For this problem, we need to consider y of p of t and y of q of t as they approach infinity. So the limit as t approaches infinity, the limit as t approaches infinity of both of these guys. So remember that y of p of t is equal to 6 minus 4e to the minus t, and y of q of t is, we solved for it in the last problem, is 3 minus 1 over t. So we can rewrite this top one as 6 minus 4 over e to the t. So as t goes to infinity, so you can kind of think of this as the t gets larger and larger and larger, what happens to our overall function? Well, e to the infinity, you can kind of just think of that as this is going to end up being infinity. And for such a tiny, tiny number compared to infinity, that this is basically just 0. So we're saying that the limit as t goes to infinity for the position of p is going to be 6 minus 0, so it's basically going to be 6. And then for the position of q, we're going to get 3 minus 1 over, we can just plug in infinity, 1 over infinity. If you compare 1 to infinity, that's basically 0. That's such a small, tiny number. So this is going to be the same thing where we get 3 minus 0, which is 3. And if you'll remember in the first part of the problem, it says that particle P moves along the x-axis and particle Q moves along the y-axis. So for the position of particle P, it's going to be around 6 as the limit goes to infinity. And then particle Q is moving along the y-axis, and it's going to be, as the limit goes to infinity, it's going to be at position 3. And so we're being asked which one is going to be furthest from the origin. And remember, the origin is down here, 0, 0. The answer is going to be particle P, okay? And the reason why is because it's further away from the origin based on what we understand about its position. So particle P will eventually be farther from the origin. This is our final answer for part D. Hopefully this helps you out with this AP Calculus problem. If you have any questions, feel free to leave them down below and I'll get back to you. And I hope you have a great rest of your day.